This is lesson 69 of the Quantum Mechanics, a mini lecture series. Thought it'd be nice to finish off the series with just some applications of quantum mechanics, some applications that I find really interesting. Quantum money is one that stands out for me. So we're all familiar with the concept of money, right? The coins and notes that sit in our wallets and pockets. But what about the idea of quantum money? So it turns out that quantum mechanics allows for the development of a form of money that would be impossible to counterfeit, theoretically speaking. Okay, particularly useful in countries like the United States, which use paper bills. Okay, not really useful for Australian currency because we use plastic bills, almost impossible to counterfeit. And so the concept of quantum money was actually first introduced by the American research physicist Stephen Wozniak in 1970, whilst he was at Columbia University. And the idea has been further developed, particularly by American physicist Edward Farhi. In 2010, he's now the chief principal scientist at Google, specializing in quantum computation, alongside Peter Shor, okay, another researcher at MIT. So here's a brief outline of their quantum money scheme, from what I understand. So let's consider the following scenario. So suppose we seek to copy some unknown quantum state. Let's call it psi. Okay, in other words, let's make a clone of this quantum state via acting on it with some operator. Let's call it C hat. Okay. Makes more sense to write it like this. I'll explain why. So what's happening is that some operator is taking an unknown quantum state, let's call it psi, and an unknown register, okay, some state A, right, and evolves it accordingly according to quantum mechanical law to get an output of two states, two of the psi states. That's all we want, right? So what's happened here is that the unknown state psi has been copied into the space held by A, right? So this is known as the quantum cloner case, okay, in that the unknown state psi has been cloned. So this is equivalent to taking x to x squared. But this, however, is a non-linear transformation. This isn't allowed in quantum mechanics, if you recall, okay? You can only have linear operations. So therefore, cloning a quantum bill is impossible, right? In the classical sense, you can copy any number of bit strings, okay? Let's call them 0, 1, 0. So a bit is 0 or 1, right? Your computer uses zeros and ones, manipulates them, and that's how it operates. You can copy as many of these as you like, right, in the classical case, and there's nothing from preventing you from doing so. But in the quantum case, it's impossible. This is called the quantum no cloning theorem. Okay, it's impossible. And using the idea of quantum money, we would be able to send secure messages like transactions as follows, right? So if a factory, let's say, could make money from a quantum system, they would know that for each qubit, okay, so instead of a bit, we have qubits. So this is this here, I should say A0 plus B1. This is a qubit, a quantum bit for short. Okay, it's both a 0 and 1 at the same time, right? Simultaneously, until you measure it, it collapses to either 0 or 1. Let's suppose the mint would know that for each qubit, if there's an eigenstate, let's call it this, sigma z. This is also known as the Pauli Z matrix. Okay, it looks like this. It's a 2x2 matrix. Then it would have an eigenvalue of either 1 or -1 if you find the eigenvalues. And when it's circulated amongst the public and then sent back to the mint can verify if the same quantum bill is as it should be. Okay, also, if a merchant was to become suspicious of potential counterfeiting, they may also be able to verify the banknote without having to send it back to the mint. Okay, so if you measure a qubit, measure a quantum state, you will get a very specific state, right? A very specific eigenvalue, a number. So that prevents people from counterfeiting quantum money, theoretically speaking, okay? The quantum system collapses when you make a measurement and you only get a very specific value. You don't get this superposition here, as it's called, a mix of 0 and 1. So that's the beauty of quantum money.